Unit 6, Lesson 7. So now, guys, we keep building on everything we've done so far, actually. We've gone from exponential and logs. We looked at how those graphs transformed. We looked at how radical and rational graphs transformed. And now we're looking at sine and cosine transform. So obviously, Unit 2 is the big building block for a lot of things we've done, right? So the good news is a lot of those rules and those things that we expect are going to be the same, okay? So in terms of vertical move, flipping, and all those things. I think it's a little bit interesting about the sine and cosine curves that they're continuous graphs. So their graphs are going to continually repeat. So we do have to look at our periods, right, and our amplitudes and stuff like we talked about last class. So in the next two lessons, we'll consider the graphs of, see this build right here? So you got your A, B, C, and then D is your transformations that we're kind of used to. Now you can go ahead and kind of make educated guesses what you think they each do, and you're probably going to be right. Okay? But these are the forms we're going to be looking at now in terms of what we're doing with our sine and cosine curves of transformations. Okay, this is the last big piece of our unit. Okay, so use the knowledge gained from the transformation unit to describe how the graph of each of these functions compares to the regular. So just these basic ones. What do you think y equals 2 sine x does? Vertical stretch. You're correct. Ooh, green. Vertical stretch of 2. Okay, so that means your sine curves are taller. Now, does that affect their period in terms of do they happen between, is it going to shrink them at all? No, they're just going to go higher. Those curves are just going to hit a higher spot, okay, but they're not going to happen more frequently or less frequently. Okay, sine of 2x, what do you think that means? Horizontal stretch of 1/2, you're correct. Okay, so a lot of these things you already know. Okay, good. Again, I'll say it. I've said it a few times. We continually keep missing it. But within the function, you flip. When you're told that's the stretch, that's the stretch. Okay, so right here, it's 2 within the function. We flip for the stretch. But if I told you it was 2, then it's 2. Okay? Okay, what about for 3? Okay, reflection over x, I heard, correct? X-axis with a vertical stretch of 3. And the last one here. Good, reflection over the y. And horizontal stretch of 1/3. One thing too, guys, is a couple of you guys still do this, and it's not quite right. You don't put the negative as your stretch, right? We don't say horizontal stretch of -1/3. We say 1/3. The reflect takes care of the negative, okay? So make sure you don't do that. Some of you guys have done that, and you try to put it in the numerical response box when, remember, no negatives go in there. So something to keep in track. Okay, which of the above example is there a change in amplitude compared to the y equals sine of x? So change in amplitudes. What's amplitude again? Right, so which one changes the height, do you think? The vertical stretch. Good. So which two affect the vertical stretch? 1 and 3. So 1 and 3 are the two that the amplitude changes. When I say amplitude, you think height. Obviously, when you hear height, vertical stretch sounds like something that would affect that, right? Okay. Good. Which of the above examples change the period? So then again, period is how often things happen. And so you can think about horizontal stretch is affecting things horizontally. So then you go ahead and conclude that 2 and 4, okay, 2 and 4 affect your period. The period, again, is how often your graph repeats. It's how often your graph repeats. Okay? Okay, complete the table using a graph calculator if necessary. So we'll go ahead and just fill these out together. We'll kind of save the graph calculator. I'm pretty sure you guys can punch these in. Okay. So complete the table. So y equals sine of x. We know the amplitude for that is 1. We know the period is 2 pi or 360. They're doing in degrees, so we'll say degrees here. So then 2 sine x. What does that become? Still 360, good. The period didn't change, and the amplitude now is 2, right? It's going up to 2 and down to negative 2. So it has a total distance of 4. Divide the 4 by 2, you get 2. Now, sine of 2x. So did the amplitude change? No, so that one's still 1 now. And we did a horizontal stretch of 1/2, so what do you think you do? Right, you half 360. Good. So you guys are getting all this stuff. And this is basically what we're going through. Okay, so that means that full sine curve, guys, now happens in 180 degrees. So it's been squished down. Okay, it happens 180 degrees, not 360. Okay, so what I'm saying is, if you're not following, your sine curve goes like this to 360. Well, now when we do the stretch like that, it's going to happen faster. It's going to go like this at 180 all the way through. So it's being tight. Okay? Negative 3 sine x. Amplitude. Just 3, right? Yep. Just 3. And did the period change? Nope. So still 360. It does, but remember it's symmetric. So it's going to, you're right, it's flipped, but it's still from negative 3 to 3. And so remember, we go, it's still going to be 3 is the amplitude. The other thing about amplitude, it'll never be negative. Same thing with like reflection, right? Okay, all good points. You guys got that? Think about amplitude as distance. Distance from the center. Okay, sine of negative 3x. So that doesn't affect the amplitude, right? So we're still at 1. Now what's that going to be? 120, good. The negative doesn't affect it. The negative will flip it over the y, but the pattern is within 120 now. So even tighter than the one I drew. Now I got a combo here. We got 5 sine 4x. So amplitude 5 happens for a period every 90. Good. 360 divided by 4. Okay. Questions? Yeah, go ahead. What do you got, Bubba? How come what?
I did 180 divided by that's why. 360 divided by
Gotcha. Yeah. The number in front of the x, the horizontal stretch? Yeah. Right, it is 1/4. And so we take 1/4 of 360, and that's 90. Right? So when you do 1/4, that actually means it's getting tighter. And if it was a fraction, that means we'd be stretching it out. Okay? Any other questions? Do you have anything back there, Aiden? Next to you do? Okay. 1/3 sine 1/2 x. So this is what I just was explaining, actually. So the 4 makes it get tighter because we're 1/4ing it. 1/2 is going to stretch it out. So your period's getting bigger. So that means things are happening slower. Okay? So that means, see how 360? If I stretch out my period, so if I do it by 2, it's going to be 720, right? So that means that the halfway mark is now 360 here. And then I come down here, it's 720 is when it makes its full sine turn. That's what's happening. So the period for this one is going to be 720. Okay? So then what's the amplitude? Yeah, it's still 1/3. It got smaller. So this is going to be an interesting graph. This is going to be a very flat graph. If you put that in your calculator, it's going to be very flat compared to the normal because it's lower and it happens like a longer time. So it would be really, if here's 1, it'd probably be like this. Like something like that. And then that's 720 there. Like 1/3 and negative 1/3. Okay? And then so then you guys get the idea the amplitude is A. And then this is going to be, how do you do that? Say that again. Yeah, 360 over B. Right? And B is absolute valued, by the way. Okay, we don't care about the negative part. The negative is just to reflect. When you do that, though, it's kind of silly because it's a symmetric graph. So when you reflect it, it's going to land on itself. So that's actually not that huge of a deal in terms of the graph. Okay? All right, cool. Would you expect similar effects in the graph of y equals a cosine b of x? Yeah, I mean, why wouldn't they be the same? Because the cosine just starts at 1, but all the stuff is going to end up being the same. So yeah, we would. Okay. Change a parameter on a. On the graphs of y equals a sine x, y equals a cosine x results in a vertical stretch about the x-axis with the following. A is greater than 0, that's a vertical stretch. A is less than 0, that's a reflection on the x-axis. Okay, these are all things we know. That's what we expected. Okay, so that we don't have to talk about that too much. Remember, like I told you earlier, vertical stretch by the factor is always the positive vertical stretch. We don't stretch negative. That just means flip. Change parameter in a for tangent. Results in a vertical stretch of factor a about the x-axis. Change the parameter for b of the graph of y equals sine b of x cosine b of x, and y tan b of x results in a horizontal stretch about the y-axis with the following. If b is greater than 0, the results for horizontal stretch are 1 over b. If b is less than 0, it's a reflection. And remember, your horizontal stretch are always going to be positive. So 1 over b also means if it is a 1/2, then that's really 2. Okay, so 1 over b just means flip. So think maybe just write a note to yourself, remember flip. Okay. All right, so here's everything we have. Kind of broken down here. So y is a sine b of x, or y is a cosine b of x. Amplitude, max minus min over 2. Period, 360 over b, so whatever is happening next to your x there. Period, or you can do in radians, is 2 pi over b, so we can do stuff in radians. Okay, so amplitude's not applicable to tangent y. Did you guys do that homework question for tangent? What did tangent do? Did you notice? Tangent didn't stop, because tangent has asymptotes. So if you didn't do that, you need to do that tangent one, or else you're going to be really lost on tangents. Tangent's completely different. Tangent is, it looks like, let's see here. Tangent is undefined at 1, it's at pi over 2. So like pi over 2, okay? And tangent's undefined. Tangent's undefined at the top and the bottom. So these are asymptotes. And so tangent goes like this. That's how tangent looks, and it keeps repeating. And so the point is there's no amplitude because this thing is forever going up and forever going down, so we can't put an amplitude. Okay, so tangent doesn't have amplitude. If you take a look at tangent in your calculator, you'll see what I'm talking about. It has a little curvature here. Okay, the period can be adjusted though, but notice for tangent, this is a big thing, guys and gals. Tangent happens every 180. It's repeated. Why? Because that's where the asymptote is. It happens at pi over 2, at 3 pi over 2. Those are 180 apart. Okay, so the tangent, it's every 180. It's going to have a its period is in terms of pi. Its period's in terms of pi or 180. So instead of all the way around, it's halfway around. Okay. All right. So hints for graphing the trig function manually. Sketch primary trig ratio, y sine x or y cosine x. Adjust the basic graph for any change in amplitude considering the max and min points. So get your amplitude so you know how tall you're going, and then figure out how wide you're going for your period. And then you could sketch your curve from there. That's kind of how you set up your graphing in terms of the sine and cosine curves. All right, let's do some examples here. Okay, consider the graph of 4 cos 2x. State the amplitude and the period. Okay, we're going to state the amplitude and period, and I'll have you guys sketch it, and I'll come around and take a look. Okay, so state the amplitude and period. So what's the amplitude? Andy, what's the amplitude? 4. Good. Okay, and then we'll say right there, Cash, what's the period? What'd you say? Yeah, it's 1/2 of 2 pi. We're in radians here, so what's half of 2 pi? Right, so your period is pi. Every pi, you're going to have a cosine curve. Okay, go ahead and sketch that. I'll pause the video here. Okay, so yeah, you'll do want to be in radian mode for if you're putting your graph calculator. The idea though is we're not, like, you can use that to check, but we want to go ahead and graph these first without, but you can use it to check. But the big thing here is that cosine starts at 1, but for this one 4 because the amplitude's 4. So we start here, and we finish at pi back to 4, because cosine starts and finishes at 1 on the unit circle. So at the amplitude of 4, it's starting and finishing at 4. Then we know that, so like when you think about this, okay, you're going around, cosine's 1 here, halfway around, it's -1. So then halfway between these two, which is 6 units, 3 units, I should be at -4. That's just kind of getting an idea of what to expect. Okay, that's like my landmarks. Now the other things is we know that, I know this is half of a half, but halfway between -1 or -4 and 4 is a 0 spot, right? This is where this one, I don't like that it's 6. That means at 1.5, because it's 3 away, it's going to go through the 0 there. And then here at 3, another 1.5, it's going to go through the 0 here. And so the curve looks like this. And then it repeats. Okay, and then goes again. So 2 pi, so that's another pi. So over here it's going to be again at 4. Halfway between these, so 1, 2, 1, 2, 3. Right there, that's my other -4 spot. And then at right there, and right there, there's my zeros. And so you kind of got your sketch here through 2 pi. Now remember, why did I graph to 2 pi? Because it told me to. It says I want to be between 0 and 2 pi. So what's important about that is that when you make the connection, our period was pi. It wanted me to graph 0 to 2 pi, so it means I'm drawing the graph twice. I should have 2 cosine curves. I have 2 cosine curves, right? 1, 2. Any questions there or confusion on that? Again, landmarks are important. Landmarks are important. Knowing that 0 and pi is my ending, okay? Halfway between 0 and pi on the unit circle is a 0, so I know halfway between 0 and 3. Everything just gets shrunk. Okay? All right, let's go ahead and try these here. Write the equation of a sine function. So now they're telling you stuff. They want you to put it into the equation. Sine function have amplitude of 2/3, so we only want 2/3 sine and a period of pi over 6. So it's real tight. Okay, that's happening really quickly. So that means we want to have 2/3 sine 6x. Or no, it's 12x, isn't it? Sorry, 12x, my bad. It's 12x. Because it's radians, not degrees. So it's 12x because if you do 2 pi divided by 12, right? Because it times it by a half. Sorry, times by 1/12. Let me back up here. We're in radians. That tells me I'm in radians. 2 pi is what I'm multiplying my horizontal stretch by. My horizontal stretch is 1/12. 1/12 times 2 pi. What's that? How do I know it's 1/12? Because what's 2 over 12? Pi over 6. Okay, so okay, I'm trying to make it pi over 6, right? What's 6 times 2? 12. Because we know that we're going from 2 pi to pi over 6. Okay, so how do you do that? So remember with the degrees, we went 360, and if it was, let's just say, okay, we have 12, right? If I was 360, I'd go times 1/12, right? Well, I'm doing the same thing for 2 pi, and I'm trying to make it pi over 6. That's why I picked 12. 2 over 12 reduces to 1 over 6. That's what they told me it should be. So it's kind of like knowing that I want to get a 6 by going from the 12. Okay? Trying to think of a better way. I know you're struggling with the radians part of it. Let's see here. So essentially what you got to figure out is 2 divided by what gives me 1 over 6. That's what you're trying to figure out. Because it's 2 pi divided by what gives me 1 over 6. So 2/12 gives me 1 over 6. So I need a 12 here.
Why can't you just simplify
To 6x. Because if you do 6x, that's 1 over 6. Now you're not at pi over 6. Because our period is not pi. Remember, 2 pi is always the full term. So we have to have that 2 in there. You can't get rid of the 2. You just got rid of the 2. So you have to think within 2. That's why I know. That's why it's 12, not simple divided by 6, like I put originally. Okay? So think about reducing. Okay? Cosine function, now degrees will probably be a little bit easier for you. Having amplitude of 3 in a period of 720. So since 720, that means that the stretch it got bigger. Okay, so we're going 3 cos 1/2 x. Because you flip 1/2, it's 2. 2 times 360 is 720. So that's since where it's stretched out. Okay, any questions? Now, this one is the little bit of a curveball. We said tangent happens in a period of what? Right, or pi, right? Because this is in radians. So now we're not doing 2 pi, we're doing pi. So tangent, you do have to change what you're thinking in terms of these are 2 pi's. This is 1 pi for tangent. That's something you just have to know. Right, so yeah, it would just be 2x. Yep. Okay, so again, how Cash got that? It's 2x because, well, what's the stretch actually? 1/2. What's 1/2 times the period? The pi over 2 they wanted. Okay, 1/2 gets you pi over 2. Okay, so that's good. That's good understanding. There's workbook problems on those, so if you're swimming in those, make sure you do some of those. Okay, got 2 more. Let's take a 1-minute break here, and then we'll get to do the next one. Okay, state the amplitude and the period of the graph. So state the amplitude and the period. So it looks like the amplitude is what? 3. Good. Amplitude looks like it's 3 to me. The period, so it starts here, finishes here. So it looks like it's pi. Okay, you guys see that? Period pi. Okay. I just see the full turn happens within a pi. That's the full curve. That's where it starts to repeat. Determine the equation of the sine function which represents this graph. So y equals 3 sine. What's it going to be here? We're halving the period. So how am I going to half the period? 2x. What's that? Sure, if you want. But it's not really relevant to that. That's a value, like an x-coordinate. So that's kind of how this is growing. But if you need to, that's fine. Okay. All right, last one here. Okay, the graph represents the effect of tides on a mean sea level over a 24-hour period. The graph has an equation, h of t equals a cosine bt, where t is in hours and h is the height in meters relative to the mean and the sea level. Determine the equation of the graph. So we have to determine this cosine curve. So for the cosine curve, we know that cosine starts, okay, so we're right here. Where's it starting here? Yeah. Okay, so it looks good. So yeah, amplitude's 4. Okay, so my amp's 4. And then what's the period here? So the period, this one looks like we're just simply, let's see here. So it should be here to here. So it's going to be, yeah, it looks like 12, yeah. So it's 12 for the the period's, that happens every 12. Okay. Okay, and so that means 12 hours. So, but we know that, so this is what you guys are struggling with. So if the period happens 12 units here, in terms of radians, what is that going to be? Not pi over 12. That's what we just did, right? It's the same one we just did. If it's 12, guys, it's 2 pi times 1/12. Right? It's 2 pi times 1/12, so it's that pi over 6 again. Because it wants to know in terms of radians how often it happens. It doesn't say that, but that's what they're actually having the key here. So they want the terms of the period for the cosine curve. So it's your understanding of the cosine curve, because we use cosine within radians when it comes to measurement of where it's at. So you're doing 12 units because it's terms of time. So 24-hour period, right? So this happens twice in 24 hours, right? Okay, so essentially what's happening is having twice in 24 hours. That's going to be happening in terms of what they're asking at pi over 6. So let's see, how can we explain that in terms of a day? So they want pi over 6. Yeah, 2 pi is 1 day. Yeah, that's a good way of putting it. If it was tangent, yeah. If it's tangent, it'd be pi over 12, yes. Yeah, if it's tangent, it'd be pi over 12. Okay, so let's look and see. So this is what they're going to have it as. Let me see if I can try to piece together the context. We're good with 4. It's going to be pi over 6 of t for time. Okay, so let's see here. Yeah, I'm just trying to think. Let's see here. All right, so we'll stop right there for the video, but we'll keep chatting here in just a second.